Good morning, everyone. Thank you for attending my presentation. My name is Andreas Michael, and I'm with Cipriana Petroleum Technology. And my title is Graphical Method for Constraining the Local Stress State in Arbitrarily Oriented Wells using Drilling-Induced Tensile Fracture Observations. Despite the long title and seemingly complex one, the concept I'm describing here, as well as the graphical method, is pretty straightforward, and it can incorporate further complexities, which is mostly where the novelty of my work lies. However, I try to keep this as simple as possible so I can at least be able to give the audience the basics so that they can use this method. And if they want to dive into more details, they can always read the literature. I have many papers, or 2 or 3 papers on this topic actually, or they are partly on this topic. From a geomechanics perspective, drilling-induced tensile fractures, or the mechanism which initiates those drilling-induced tensile fractures, is identical to that of the initiation of hydraulic fractures from open-hole wellbore sections. Nevertheless, observation of those drilling-induced tensile fractures can be a valuable diagnostic tool because they can be used to constrain the magnitude of components of the local in situ stress tensor, local to the well from which those drilling-induced tensile fractures are observed. Those drilling-induced tensile fractures, they leave a distinct signature on the image logs, and they have been used in the past to constrain particularly the magnitude of the maximum horizontal in situ principal stress. That would be the most, by the maximum I mean the most compressive, the SH max. It was successful particularly in West Tuna area of the Gippsland Basin in Australia. And there was a paper by Nelson in 2005, very famous one, about that particular application of a similar method. So let's start. Like I said earlier, drilling-induced tensile fractures are observable from image logs. They are located orthogonal to wellbore breakouts, and the way you can identify them from those logs is they leave a dark, normally darker imprint than the breakouts, and when you compare it between the two, the signature of the drilling-induced tensile fractures is also narrower, so narrower and darker. Because most of image logs are taken from vertical sections of wellbores, and in most areas around the world, the stress state is approximately Andersonian at the depth that we are interested, which implies that you have one in situ principal stress fully vertical, VSV, and 2 horizontal stresses fully horizontal, SH max and SH min. That means the vertical section of the well is parallel to SV. This promotes the 2 extreme orientations of those drilling-induced tensile fractures. The first is longitudinal, which we see on the left image log with the red, where drilling-induced tensile fractures are initiating axially with respect to the wellbore. And the second extreme drilling-induced tensile fracture orientation is transverse, which is shown on the right image log with blue, and that's where drilling-induced tensile fractures initiate lateral to the wellbore or orthogonal to the wellbore. The orientation of drilling-induced tensile fractures is to a huge extent dependent on the local stress state, along with some drilling parameters such as wellbore pressure, and therefore we can reverse engineer the problem and use observation of a certain orientation of drilling-induced tensile fracture in order to back calculate the stress state, considering that we do have some idea of some stress state components from league of testing data for SH mean and overburden calculations, for example, for SV. Some basic geomechanic concepts that we need to have in mind before diving into this topic is related to the stress state on the wellbore radius. We know that the presence of the wellbore, drilling a wellbore, disturbs the stress state surrounding the wellbore in a way that the stress state in the near the stresses, the pre-existing stresses, what we call the in situ principal stresses, those are the vertical SV and the horizontal SH max and SH mean, SH max always bigger or equal to SH mean, are no longer dominant in this near wellbore vicinity. Instead, we have a set of three new stresses which act in cylindrical coordinates and dominate this near wellbore vicinity. Those are the blue axial stress, sigma ZZ, the red tangential stress, sigma theta theta, also known as hoop stress, and the green radial stress, all acting in cylindrical coordinates, as we see here in this schematic. And also, the value of those stresses will vary as for more exotic orientations of the wellbore. And as you move away from the wellbore, you also have shear stress. However, for this problem, we only care about the values of those stresses on the wellbore radius. And on the wellbore radius, there is no shear stresses. Now, the range of stress states which can occur in the Earth's subsurface can be visualized in a very simple two-dimensional plot called the allowable stress state diagram. Sometimes this is known as MAP. This has SH max normalized by SV on the y-axis and SH mean normalized by SV on the x-axis. The dotted diagonal is the line of horizontal isotropy, where SH max is equal to SH mean, and the solid dark lines are drawn to indicate the frictional limits. Any stress state outside those bounds is virtually unstable, because if a fault exists in those stress state conditions, it will automatically fail in shear. There will be fault slippage, which is basically an earthquake. The polygon enclosed by the frictional limit lines and the dotted diagonal, it represents the range of stress states that you will expect to see in the Earth's subsurface under the conditions used for this plot, like the frictional limit value of 0.6. We can take this plot and add two lines to it. The cyan line for the stress states for which the axial stress is equal to 0, and the green line for the stress states for which the axial and tangential stress is equal to 0, are equal to each other, sorry. for a given wellbore pressure, which for this problem we assume to be hydrostatic, 0.3 psi per foot. The area within the polygon behind both of those two lines, I shaded blue, and this represents the range of stress states in which transverse drilling-induced tensile fractures will be promoted if we drill in those cases. And the remaining of the polygon I shaded red, excuse me, to imply that or to signify the range of stress stage in which longitudinal drilling-induced tensile fracture initiation will take place at the given wellbore pressure gradient or higher. The size of those regions is dependent on various geomechanic and drilling parameters. For instance, one of them is wellbore pressure. As wellbore pressure increases, as we see here, from 0.33 psi per foot, which is indicated with the dotted line, to 0.53 psi per foot, which is indicated with the dashed dotted line, the blue region decreases. Therefore, we see that overbalanced drilling makes transverse drilling-induced tensile fractures even more rare compared to longitudinal. The value of Poisson ratio affects the blue region in a slightly more complex way, but the conclusion is that higher Poisson ratios lead to bigger size of the blue region. And here I will use an example, a very simple example, to show the graphical method of constraining the SH max from information from a vertical well. We assume hydrostatic pore pressure and 0.6 psi per foot for wellbore pressure, which is about the fracture gradient of the Barnett shale, which is fairly low actually. We draw those lines, the green line and the cyan line, and then we have another line, the magenta line. This line is indicating the SH mean, and the value of SH mean is easily estimated using Lickhoff testing data. Now, the region enclosed by those three lines, I shaded it in yellow, and this signifies or indicates the range of stress states that can take place in this well. And the only thing you have to do from here is go to the vertical axis and read the range that SH max can take, either considering that you observe transverse drilling-induced tensile fractures, which would be the yellow region here, or if in case you observe longitudinal drilling-induced tensile fractures, then the range moves from this one to this one here, from the minimum to the line of horizontal isotropy, which will be equal to SH mean, which shows you how longitudinal drilling-induced tensile fractures can still constrain the value of SH max, but not to the narrow range change that transverse drilling-induced tensile fractures will. In conclusion, we can use allowable stress state diagrams to constrain components of the local in situ stress state, such as SH max, higher Poisson ratio, and low wellbore pressure increases the size of the blue region, which means that more promotion for drilling-induced tensile fractures. Because transverse drilling-induced tensile fractures are rare compared to longitudinal, they are more useful as diagnostic tools. And a graphical method is applied to any geomechanics model as long as you can create a closed form relationship for the axial and tangential stress on the wellbore radius, which is where the novelty of my work lies.